Now, without further ado, let's move to introduce our speakers, and I invite the first speaker, Jeremy Brown, to join me in the stage.
Good afternoon, everyone. Thank you, Claudio, for the introduction. Just a little side note also from my bio, I went to undergrad at Morehouse College, which is a HBCU maybe about 10 minutes down the street from here. And so it's always nice to come back to Atlanta, and I'll just say that, maybe 20 years ago when I was a student at Morehouse, never would I have imagined that I would have the opportunity to stand on the stage in front of my peers and have the opportunity to talk about research that I'm truly passionate about in the area of prosthetics as a tenured professor. So I'm immensely humbled and honored by this opportunity and grateful to the organizers for the invitation to come speak. So I'm going to talk to you a little bit about work that I've been doing really since I would say I really started in the research domain as it relates to human-robot interaction and prosthetics. And so to motivate the talk, I'm going to show you sort of a juxtaposition between two time periods. The first is 1921, and what you'll see in this video is an individual using what we refer to as a body-powered prosthesis to perform a series of tasks that one could argue are extremely dexterous. In this case, taking a hammer and driving a nail into a piece of board. You'll see in a second that he'll change the end effector out, put on a manual drill, drill into the wood, and then really quickly it's going to shift over and you'll see another individual using a different arm to do what we kind of consider activities of daily living, maybe with the exception of smoking, but being able to pick up an object, drink from a glass of water without spilling it, right? And now fast forward almost exactly 100 years, and the work, incredible work done by Ad Spears and Aaron Dollar showed, essentially that in today's society, when we think about sort of the state-of-the-art in prosthetic limbs, what we often see is that the limb is actually not being used as the primary tool to carry out the task. It's oftentimes playing a very supportive role. It's not, I think Ad's work showed that the majority of the tasks that the limbs are being used for is actually non-prehensile, so no grasping and manipulation, which is a really far cry from that video you saw almost 100 years ago. And so the question is, why is that the case? And I think there are many in this audience that would argue that it's due to hand design, right? We don't really have good mechanical design of our devices, and I would say that there's definitely room for that. But as you've probably seen from the conference here, there are plenty of individuals working in sort of creating good functional hands that have high degrees of freedom, sometimes even more degrees of freedom than our natural limbs. I would argue that it comes actually, the larger reason that we don't see this adoption or this good use comes from the lack of good sensory motor control in these devices. So let me give you a quick overview of what sensory motor control is. Assume you want to pick up this green circle or object that you see here. Well, what happens is you first recognize the object by sight most times, and then a series of commands that we often refer to as our efferent signals come from the brain through the spinal column out to the periphery, cause the limbs, the muscles in the limbs to contract, you reach and you grasp it. And so how do you know that you've actually grasp this object? Well, in addition to the efferent side, there's this other signal command that we call the afferent signals, which give us all of this information, like you've made contact with the object. It tells you how hard the object is, how stiff it is, whether it's fuzzy or whether it's cold. And it's that information that really drives our ability to do dexterous manipulation in the environment. Claudio already alluded to this. Our haptic sense can be thought of as broken down into two major modalities: cutaneous sensations, which come from the mechanoreceptors that are embedded in our skin, and then of course the kinesthetic sense, which comes from the muscle spindles and Golgi tendons that are embedded in our musculoskeletal system. As roboticists, we've already built robots to sort of replicate these sensors oftentimes, so you're already probably familiar with what they do. The problem is, how do we extend them into the prosthesis? Touch is extremely important. We use it every day. We use it all day. Many of you who are watching the screen, but also fidgeting with your laptops or screwing caps off of bottles or taking pictures, are using touch at this very moment. If you don't believe touch is important, I'll take a canonical example that many in the haptic community probably use and overuse quite often. This is an individual who's trying to take a match out of this matchbox and strike it and light it. But prior to doing the task, they applied local anesthesia to the fingertips, and so they can't feel what's going on. The end effector in this case, the hand, is perfectly intact. Vision has not been impacted, but this just lack of haptic information is strong enough that it really drastically degrades a person's ability to do what we would think of as a very simple task. So again, as I said, what do we do when we talk about a prosthesis, right? We know we have good sensory motor control in our natural limbs. In the case of an amputation now, that good sensory motor control only extends to the most distal part of what we could refer to as the residual limb. And so when you put a prosthesis on someone, how do you take that sensory motor loop and extend it all the way out to the end of the device, at the end effector? And so I've spent, almost 15 plus years now working on trying to answer this question, starting as a graduate student at the University of Michigan with Brent Gillespie, where we had this idea that, well, a body-powered device works really great because this Bowden cable gives you this inherent force reflection. Is there a way that you could combine that with, a myoelectric device and get the benefits of both worlds? And we've found some, a modicum of success in that regard. We even sort of, one of our studies early on tested this idea of the utility of body-powered or force reflection in a prosthesis, and we showed that actually when you turn the feedback off, performance degrades just like it would in a myoelectric device. And so what I'm hoping to talk, for the rest of my time here, I've got three what I call central tenets that I think my lab sort of operates around as it relates to trying to improve the utility and function of prostheses for individuals who wear them. And the first one is that feedback is a means to an end. In one of the earliest studies we did in my lab, my student, Dr. Neha Thomas, sort of challenged me and said, well, you've done all this work, adding exoskeletons to people and showing that force reflection really does yield benefits, but is force reflection really the best way to give feedback? Now, the mechanical designer, mechatronics engineer in me said, of course, because I love exoskeletons. They're just cool. They're complex. The idea of coupling dynamics of the human's body to the robot's body is just very interesting from a scientific and intellectual perspective. But she said, what if we tried vibrotactile feedback? What happens if we compare someone getting force information from their prosthesis to a vibrating cue, as well as one from an exoskeleton giving force reflection, and how do both of those compare to the natural limb? So we built what became one of the first mock prostheses in my lab. We call them a mock prosthesis because a lot of the work we did early on was with individuals without limb loss. And with this exoskeleton and sort of standard C2 tactor, we ran a study, very simple one in this case, looking at object discrimination. I give you an object that has a stiffness, it's not visually discernible. Can you differentiate that object from another one? And by and large, what we found is that yes, with feedback, both feedback in this case, vibration and force, or force reflection, or joint torque feedback as we called it at the time, it did better than not having any information at all. But when it came to comparing those two together, we saw no difference, right? So all of this work that I, sort of prophesied about in my graduate work around exoskeletons are the key and force reflection is the way to go, we showed that actually it's not that much better than just sort of putting a tactor on someone and buzzing them. The information itself is what's powerful, and however you get it, if you can interpret it, you can make use of it. The second one is that cognitive load is approximately equal to metabolic cost. So I actually started off in the lower limb community where, we were designing prosthetic feet, and oftentimes the unit of measure that you would use to decide if your design was better than sort of the standard is to put a metabolic mask on someone, have them walk on a split belt treadmill, and look at their metabolic rate of consumption, right? It's this sort of cost of transport. In the upper extremity, we don't really have, this sort of gold standard measure. And I know that many in the community that may argue that metabolic cost may not be the actual, sort of gold standard. I think Elliot Rouse has done some amazing work looking at other cost functions that people use when they think about using an external device. But can we find such a measure, sort of for upper extremity use? In my lab, we think that is cognitive load. Because really and truly using a device, it's not just the performance that you are able to produce with the device, it's the mental effort that it takes to achieve that level of performance. So using our same prosthesis with vibrotactile feedback, we ran another study where we compared that against the prosthesis without feedback. And in this case, because we had individuals without limb loss, we compared that to the natural limb. Again, we were looking at task performance, simple tasks. I give you an object of different stiffness. Can you differentiate them? Can you identify them? But here we also looked at the mental effort that it took to do that task. And so what you really want in this case is that the ideal device, you see a drop in mental effort, and you see an increase in performance. And we call this neural efficiency. And this is a term that was actually coined by my colleague Hassan Ayaz at Drexel University, who was a collaborator on this research. So using our standard mock prosthesis that I showed you on the last slide, combined with this neural imaging technique that we call functional near-infrared spectroscopy, which looks at the hemodynamic response in the prefrontal cortex, we're able to get a measure of cognitive effort. And what we found in this case is that haptics does lead to a significant increase in neural efficiency, better performance, lower mental effort than actually using the prosthesis without haptic feedback. Still, at the same time, because these are individuals that had their natural limbs intact, the natural limb is light years ahead of what we're able to do with sort of, what I call state-of-the-art research prostheses. So we've got a long way to go, but this feedback actually is now showing a benefit not only in task space, but also in the cognitive and mental space as well. And then the last thing I'll talk about very briefly is that biologically informed design works. So what you see on this slide is the bionic hand on the left by Autobot, sort of juxtaposed against the natural limb. And while they very much so look similar in form, they're very different in terms of function and how they are actually actuated. When we look at the natural limb is actually actuated by a series of tendons. In fact, it's this sort of agonist-antagonist tendon structure that allows us to not only control the endpoint position of the digits, but by means of co-contraction, actually control the endpoint stiffness of the digits as well. And we don't really see that level of impedance manipulation in our current set of commercial prostheses. So a couple of years ago, I had a student, Ethan Miller, decide he was actually motivated a lot by the work of Aaron Dollar and some of the under-actuated hands and Ashish Deshpande and his ACT hand to come up with a fully actuated tendon-driven prosthesis. This is our first prototype. And we showed, with this tendon-driven device that you actually get really good control affordance out of this device with the individuals that were able to use it. We've now sort of moved on, one of the problems that we ran into with this device is actually hand design now becomes a problem. At the beginning I said hand design is not the problem, but as you begin to, sort of improve and upgrade these devices, you have to go back and change things. And so here, hand design is something that we've just sort of gotten into, where we have a process now where we actually make prosthetic hands that are modeled exactly after their biological counterparts. And we can do this for individuals with intact hands as well as individuals with limb loss, in this case, a partial hand prosthesis. And what we've been able to show is that with this new hand design, we are able to actually control and get better performance in terms of activities of daily living. Okay, so with that, I will stop, and I don't know if I have time for questions, but yeah.
Yep, thank you. So we do have time for a couple of questions. So if you have questions, please stand up and move towards one of the microphones. Don't be shy. So I will ask. Oh no, please. Perfect.
Thanks a lot for that wonderful talk. I really like this concept of mental effort or mental efficiency. I imagine that's something that the user develops as time goes by, as he or she gets used to the prosthetic device. Is that something you looked into or have considered?
That's a great question. The answer is I completely agree with you. I think mental effort is not a static concept. It dynamically changes, right? I mean, for those of us who drive cars, right? The first time you get in a car, your mental effort is probably extremely high, right? You're concerned about every little thing going on in the vehicle. And as you begin to drive day after day after day, I would say your mental effort goes down so much so that people decide to take out their phones and text while they drive, right? Because you've got this, you think at least you've got this cognitive resource that's sort of freely usable. The same thing happens in the prosthetics world. When you look at individuals with limb loss or prosthesis users who use their device day after day after day after day, I would say that their mental effort is much lower than someone who, let's say, first is outfitted with their prosthesis. And so I think what we need, what we're hoping with this work is to sort of justify the need to do more longitudinal studies to say, how does it change? And are there ways that we can use feedback or other forms of control to actually speed up that learning process? Because maybe it does start high, but if I give it to you in a way, that sort of augments you fast enough, maybe it drops off very quickly, much more than sort of a natural, would normally happen without the feedback.
Very quickly.
You compared metabolic load to cognitive load, and to piggyback on that question, is there a divergence? So as someone gets more familiar with a limb, does the cognitive load go down, but does the metabolic load stay roughly the same?
Yeah, so we actually, I mean, the two in this case are actually somewhat intertwined because the metabolic load here is actually looking at the oxygenated, deoxygenated hemoglobin in the prefrontal cortex. And so they're roughly tied together, right? The more you're thinking about something, the more the brain is pumping oxygenated blood into that region of interest. So, you know, in this case, cognitive load going down means less oxygenated blood, you know, likely going to that region as well. Thank you.
Great, so let's thank again our speaker, Jeremy.